Okay, everyone, I'm going to try and go through problem 20.11 or 25.11 relatively quickly here. So if you need background information, I would check out the lecture slides. So if 4% of a population in equilibrium expresses a recessive trait, what is the probability that the offspring of two individuals who do not express the trait will express it? Okay, so what does that mean? What is the probability of individual one mating or reproducing with individual two to produce offspring with this recessive trait? So essentially what we need to figure out is, so individual 1 and individual 2 do not express the trait. In order to produce an offspring that expresses the trait, so each individual must be heterozygous, right? Because that's the only way that you can produce an offspring that is homozygous recessive for the trait. So what we know from the problem is that 4% of the population, of a population, express this trait here. So 4% of the population express this recessive trait. And this is the population is in equilibrium for this trait. So let's see. We need our two equations that we use when we're talking about population genetics. So P plus Q equals 1, where P is the frequency of allele number 1 and Q is the frequency of allele number 2. We're going to say big A for allele number 1, little a for allele number 2. So those are the allele frequencies, and then we have our P squared plus 2PQ plus Q squared equals 1, and these are going to be our genotype frequencies. So this is going to be the frequency of the homozygous dominant genotype, frequency of the heterozygous genotype, and the frequency of the homozygous recessive genotype, which we already know from the problem to be equal to 4%, or 0.04. So we can determine Q now, right? So Q is just going to be equal to the square root of 0.04, which is going to be equal to 0.2. Okay. So now that we know the frequency of Q, or the little a allele, right? So if Q is the frequency of the little a allele, we can figure out P now from this equation up here. P plus Q equals 1, or P plus 0.2 equals 1. So P is going to equal what? P is going to equal 1 minus 0.2 equals 0.8. Okay, so now we have the frequencies of the P allele and the Q allele, or A and little a, in the population. So it's going to be 0.8 and 0.2. Now we can figure out the genotype frequencies of all these guys right here, right? So we are mostly interested in just this one right here. So 2 times P times Q, 2 times 0.8 times 0.2 is going to equal 0.32. So 32% of the people in the population should be heterozygous. Big A, little a. Okay, so we're also going to want, now this is the genotype frequency of the heterozygotes, and we already know the genotype frequency of the homozygous recessives from the question. Now we also need to calculate this one right here, and this is pretty easy. This is going to be the frequency of the homozygous dominants. So we already know the frequency of P, the big A allele. It's going to be 0.8, so 0.8 times 0.8 equals 0.64. So we know the frequencies of all these different genotypes in the population. And I always have this here, don't I? For those of you who've been looking or watching the YouTube videos. I cut that out of there. Okay, so we know the genotype frequencies of all these in our population. So AA, homozygous dominant A, is 0.64. Heterozygous is 0.32 or 32%. Homozygous recessive is 0.04, and we know these should add up to 1, and they do. They add up to 1. Okay, so we need to know the probability of individuals with these genotypes right here coming together to produce an offspring with the recessive genotype. So these genotypes here make up 32% of the population in total, but they don't exactly make up 32% of the population without this phenotype, right? They only make, let's see, if we assumed out of a population of 100 people, 64 of them are going to have two big A's. 32 of them are going to be heterozygous. 4 of them are going to be homozygous recessive. So we are only interested in these right here because we can tell these genotypes. So we want to know what percentage of these 96 individuals here, 64 plus 32, are likely to be heterozygous. So that's easy. So that's 32 divided by 96, and this is going to equal 0.333 forever. Okay, so take 2 people at random from the population with a normal phenotype, not the recessive phenotype. There's a 33% chance that they are going to be heterozygous. There's another 33% chance that the other person, this couple here, of this couple is going to be heterozygous. So 0.33 times 0.33, this is the probability that these two are going to come together. That is going to be equal to 0.1089% chance that, or 10.8% chance, 10.9% chance that if 2 people mate that they will be heterozygous carriers. Now, of all the progeny these people have, right, you can do our Punnett square, only 1/4 of them are going to be homozygous recessive. So we multiply that by 0.25, and we get our answer, which is approximately, let me see, 2.7% about. Okay, so that's the answer to 25.11. I don't think I'll do any more YouTube walkthroughs unless someone requests me to do one for one of the other Chapter 25 or Chapter 20 problems. So make sure if you want me to do another one, you email me, and I'll put another video up. Okay, see you in class on Thursday.